Mm, Guys, if you are ready, we might look at the examples here. We looked at the example in the figure 5.3, weighted importance sampling and ordinary importance sampling, the difference between them last time. And now I just wanted to check a couple of things here with respect to the infinite variance and the things that uh, we got right or not, considering the possibility of transitions. Uh, in the example 5.5, that this is the simple MDP that they have constructed. I will try to annotate and give a brief representation of what it is doing. This is the starting state, and there are two trajectories here, two ways to reach the goal. One is this, take a left, and uh, from this node, take a action with this probability, point one, onto the termination here, and the right one here. So this is the two conditions that we had, and based on this, we uh, gave an example of this is the line which is with respect to the correct estimate of the gamma that we want to reach to. So here we are trying different. Okay, this is for okay. This is with respect to the convergence uh, in the number of episodes that we want. So as you can see, with the one state MDP here that we have, one state MDP after importance sampling, uh, the variance is infinite with respect to uh, as you can see from this graph here, it's not converging to this line. And this for the off policy, first visit MCs. That was the method that we had. So uh, this was the result uh, of the target policy that we used this way. We considered the left one. Uh, uh, so this was the target policy that considered always the left one. Uh, so we do a graph with respect to the Monte Carlo estimates uh, in the 10 runs of different values. Uh, yeah, these were the results here. Other than that, if you have any queries here, so these are the 10 independent runs, and it's converging approximately here. My example is still running. I ran it to 10 to the power 6 episodes in the log scale, so it might take a bit of time, but yeah. And this was uh, the other thing was the weighted importance sampling algorithm that we had. That gave an estimate of 1 with the left action here, forever. But yep, here we do not have the one. Uh, uh, if it uh, if it's consistent here, the weighted important sampling uh, produces uh, only the returns consistent with the target policy, and all of those will exactly be one if uh, those are considered here. But uh, that's not the case in um, uh, that's not the case here because of the variance. Please feel free to interrupt me in case of any queries here. So this is the simple derivation of the uh, values that is being used in this graph here. If you guys are unfamiliar, this is the expected square of the importance sampling scaled return, which has been taken here. So target divided by the behavior and the return. If the return is 1, so this factor can be ignored. Uh, and this was a derivation with respect to the uh, uh, opening up of the loop here. Uh, so the length is 1 episode, the length is 2 episodes, and the length is three episodes long here. So yeah, that was the difference here. And these are three queries which we had to look at: the 5.6, the 5.7, and the 5.8. Uh, this is the 5.6 was how do we have action values? How do we calculate action values instead of the state values here using the B? Uh, Here we have, I think so. I have the slides open. Mm, let me. This is upon the variance of policy predictions, importance sampling. So insta prediction and submit return lambda. I think so. The implementation we had with respect to the value estimates can be changed uh, with the Q values, the action values here. And as we have alluded to in the previous example, so uh, that's that. And here the actions will be included with respect to uh, the weighted importance sampling which we had accumulated upon. So instead of the policy, instead of following the policy B to estimate the VPI, we will be using the Q term. So yeah, let's the max of this. So I should have prepared for them earlier. But yeah, there are some solutions here. To peek. What is the exact formulation that I'm looking for? But, yep, as I thought with the TS of A, they're just changing the state and actions here. So yep, uh, this was the optimal value function. Instead of this, we might induce an optimal queue action, uh, which we can be used to derive this. Uh, just like we have the uh, 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 V star tilde. So we can. I think so that this exists too here. Uh, Other than that, mm, move to 5.7. 5.7 ordinary importance sampling method. Why for the importance sampling increased and decreased? Why do you think it happened? Okay, this is with respect to the graph for the importance sampling method in figure 5.3. Okay, we discussed about this last time. So figure that we drew with respect to the random estimates that it takes. Importance sampling only uh, uh, taking the weighted average sum of the previous. That was the difference. And the 5.8, we had the results with the example 5.5. Using the first filter MCs, whether the initial was used on the same problem, would the variance of the estimator be infinite or not? Uh, and this will be the variance. Uh, it always is derived from the mean, so uh, it cannot be infinite because it will try to converge given certain number of time steps in the future. But there might be cases, as they have alluded to here, uh, likely in the first visit MCs, after a million episodes, I think so they are unable to converge. So, mm, yep, that is the diagram. This is the thing that we are discussing. Uh, this is from to the 10 to the power 6 a log scale that we have taken. Convergence here, yeah, it tries to, but the variance is still large with respect to every episode that's happening. Uh, Every visit method, because yeah, those durations. Yep. So any queries here? Okay, like I think so. Everybody understood everything. So okay, this was with this little weighted thing. Now we discussed this incremental implementation uh, last time with respect to the CN. What the difference was uh, here in exercise 5.9 we were told to use the incremental implementation for the sample averages described in section 2.4. So we try to go back to section 2.4. So here, this was a formulation of the new estimate that was given by the old estimate was the step size times the target minus the old estimate, which reduces the variance, which is the error in the S estimate, and we take a step. So if you guys are unfamiliar with this, I'm gonna try to uh, give a simple explanation of this. If you guys want to, please feel free to jump in. Okay. So here in the 5.1, what uh, this exercise is trying to say is this: we have to change this according to the incremental changes that we have seen. Uh, or that it's a simple. What's the slide? Yeah, this is the incremental mean and the incremental Monte Carlo updates. So we use these equations here. Uh, since this will be in this example, the first method, uh, uh, this is the first method, and for the every visit MCs, we just removed this statement, and we here we might just uh, append to the return. So this equation we will replace here, and we will get that. Uh, I think everybody gets that. If not, yeah, please feel free to jump in. Uh, for the exercise 5.10, it's saying that derive the weighted average update rule 5.8 from 5.7, following the pattern of the derivation of unweighted rule. So, yeah, this is with respect to since this This was the equation uh, with the corresponding random weights and the sequence of returns that it had. Uh, um, I think so. They use this uh, for the on policy Monte Carlo methods. Mm, so for that derivation, I think so. I might have to refer to the weighted average. What's that here? Uh, pattern or derivation of the unweighted rule. 2.3. Okay, Qn 1 plus 1 by n Rn minus Qn. So it's kind of like the same here, but uh, we have to replace these terms. I think so. That's a very good. Implementation here. And, now, if anybody would like to give their inputs on this, if you guys can see, that's the derivation that I was kind of like referring to. And equation 5.10. Oh, we lost it. Let me get back. Let me get back to 5.10. 5.10. Yeah. Yeah. So that's the derivation. I think you guys are familiar. Uh, if not, if you have any problems, I will try to give uh, it in the chat so you can look at this. So the derivation will be same, just the pattern is different with the changes in the unweighted rule example from 2.3. So yeah, I think so. Everything is clear to everyone. So now moving forward. Just somebody is asking any queries. Uh, 5.7 had an off policy Monte Carlo control. Here we use the policy to generate the behavior known as the behavior policy. We talked about this last time too. And we for estimating the pi star and the q star. Uh, uh, what's the greedy policy with respect to the Bellman backup? The Bellman equation that we had. Uh, and but here the B is assumed to be epsilon soft, uh, the behavior policy, and mm, they follow the yeah.
So just about that very quickly, I'm perhaps missing something.
Uh-huh.
So the target policy is the one that gets updated. Um, so that policy is continuously changing and adapting to the environment. Then why is that considered the deterministic one?
Since the past update, the past policies is being deterministic. I didn't get you.
Yeah, I'm wondering what they mean by deterministic. Um, okay,
Okay,
yeah. So there won't be any epsilon exploration in the target policy. Is
yeah,
that correct?
yeah, yeah. There won't be any stochasticity included.
Mhm.
From your environment. So if we look at this algo al- algorithm here, we can see that the uh, the policy that we have that we initialize with is this is the arg max of the q values of the state action pairs. So here the uh, uh, how do I say it? The try to annotate. So this is the q values that we get, and since this is the weighted importance sampling, so uh, we are choosing B here to be epsilon soft. This is the B, and which is kind of like uh, how do I say it? It depends upon uh, the this factor. This W is totally involved in the in determining our C, and hence the Q with respect to the weighted ties. But to answer the your initial query, this is not uh, uh, how do I say it? Deterministic. And sorry, this is deterministic because we are not including any uh, 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 noise, as you say, or the estimates are not being sampled according to some approximations. So it's
Oh,
the
okay.
true, yeah, it's the true values. Uh,
Mhm.
yeah.
The yes, because using the cumulative of the entire um, sample.
Yep. Yeah. With respect to those episodes.
Yeah, I guess just wondering why that's useful. I'm still trying to get my head around why that's useful.
Yeah,
So
that's kind of like you can think uh, in the from a control perspective. Even I do not have much experience there, but this is required because uh, uh, how do I say it? In my limited experience, they always try to uh, uh, get particular, because the control in control problems we always have a bound. I might be a bit off here or a bit wrong here, but uh, in the control problems we always have something to choose from with respect to uh, uh, the off policy methods like in robots. So uh,
Mhm.
uh, so we cannot just uh, mm, try uh, some how do I say it? Uh,
I I guess this is specifically for training, right? So learning a policy.
hmm, hmm, hmm,
Um, so behavior would sort of dictate sort of um, how you work in that kind of simulation or whatever, and you're also doing exploration as well. But the target policy is the actual outcome of that, maybe.
hmm, hmm, hmm.
But
Yep.
that separation is
Yeah. Let me. That completely makes sense here. Uh, mm, so yep. This was the off policy control, which David Silver uh, gave the lecture upon. And so from here that we can see it, he also gave some pointers as to why for the Monte Carlo control uh, we use deterministic as opposed to some kind of a stochasticity too. Uh, yeah, but yep, you are right in the sense that uh, 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 we have those bounded how to say it, variances in or I might be using a wrong term here, but yeah, uh, uh, there are a couple of other advantages to it. I will post it after the call in the Slack with respect to this particular query. Thanks.
cool. Sounds good. Yeah,
Yeah.
thanks.
Okay. So now let's now look at the racetrack programming example. Uh, uh, so yeah, you can see this guy here. After the speed heat map after 100 episodes, uh, 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 each episode taking 1,000 actions with respect to it. Uh, there's racetrack programming example. Uh, so yep, it's the exercise 5.12. Uh, Here we have tried to simulate this figure 5.5. Uh, I think if you guys are familiar with it,
So I just had a thought. So about the separation, it might be because the target policy, we don't want to bias it to sort of experiences that aren't really that significant. If that makes sense. Because an experience, from my understanding, it has more importance if there's a big difference between the policy pi and the policy b.
Hmm.
So that fraction, um,
Mm-hmm.
if they're both the same, then you'll get 1.
Mm-hmm.
But if they both sort of deviate from each other, then you get some larger, smaller number.
Yep. That. Uh, but that number also will try to determine the next uh, state that we try to choose. So, based on the optimal conditions of uh, the so I was wondering if that uh, also map to the current bounds of that particular state and action pair that we have, and uh, whether that weights try to give because looking from sarcastic point of view, if suppose we tried that, they might have some sort of a noise that might try to improve un- up until a certain point at and after that point it might uh, 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 how does it uh, uh, have a nosedive with respect to the actions and the states that it
Mm.
so, selects. So, uh, with respect to reaching that state a bit earlier, that optimal policy that might have some advantage, but yeah, currently I'm not sure. Uh, uh, at this present time,
Mm.
I had
You know,
to do, yeah.
so if you have no, I just it's just to have a discussion. So like if you have an experience that's very different and it causes as you said, like high variance, like it deviates a lot, right, from
Mm-hmm.
what your policy is used to, but then you
Mm-hmm.
update that same policy with that new experience, you're going to make your learning unstable. So instead you update the target. I think maybe but
Mm-hmm. Mm, yep. Mm,
cool. Yeah, we'll just have to do more reading. But please do get back. Yeah, I really appreciate it. Actually.
yep. 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 So this is with respect to the figure that uh, uh, we had in the 5.5. That's the left line, uh, the starting line. So this is the number of state spaces, the number of actions that it can uh, uh, our agent can roll in the this is just a tabular representation, uh, but yep, it's kind of like interesting. So yeah, and this is the right map, if you can see the with respect to the finish line, a couple of right turns for the racetrack task. So uh, uh, these are the states from 0 to 30 on the y-axis, from 0 to 16 on the x-axis. You can see the 30 cross 16 uh, and here it's approximately 28 cross 30. Uh, Now this is the racetrack. Uh, this is the kind of like the speed heat map, uh, which is showing a couple of right turns. So so these are some simple examples. Uh, we try to compute the optimal policy from each of the starting states. The trajectories, I think so, that we will get. Let me try to get a viewpoint of the optimal trajectory that we had. So this will take a bit of a time. Uh, I haven't ran this earlier, so I apologize. But yeah, this is the optimal trajectory with respect to this example. So this it's still computing. If I can show you guys the compute how it's being done. So this is after it has taken one episode here. Uh, it's computing. You can see the trajectory that's being generated here with respect to a particular uh, uh, when it is taking how do I say it? Mm, when our agent, let me try to draw it. It will be the best presentation of. Yep. When our agent tries to reach here, it will be sent back here. Action, action, action. So it's, yeah, you can understand which kind of a uh, it goes here. So these are these trajectories which are being generated. I think so. Everybody understands it, but yep. If you guys have any queries of how this algorithm works, we can go to the nitty-gritty with respect in the code. We can look at the data structures with respect to how in the tabular settings this kind of thing goes on. But in the real world, we use some kind of convolutions, convnets, or some transformers nowadays to achieve the same. So, uh, yeah, we can experiment with that too. There are multiple environments nowadays which we can use to do that. So, uh, this is the optimal trajectory that it I think so took uh, three or four iterations to reach. So this is the figure that we get from start state to the end state here, and this is the velocity, the lighter values show a higher velocity as opposed to the darker. Uh, Initially, it starts small, then yep. So yep, and they gave restriction here with respect to the velocity and then the rewards, which has 3 cross 3 actions that it could take, our agent could take. So, uh, yeah, do you guys have any queries here? For the trajectories that we are trying to uh, go through from the start state to the initial state uh, in the race map that we are trying to give. These are the number of training maps that we had. So uh, in this case, it's uh, post, we'll have to debug this. Mm, debug configuration to get, or I can simply try to print it. That's much more simpler. Number of initial states with respect to the race map, environment that we are trying to select. So the concatenation value, because this might be taken as a string. There's a list. Just a second. Yep. I think so. I have some problems with my ID. It's just not willing to take the debug parameters right now. But yep, it's approximately the list that determines the. Was hoping to show in much greater sense. with respect to the visualization of these states. But anyways, the discounted aware importance sampling. Uh, it's just the discounted aware importance sampling that we had was with respect to. It's finally working. Uh, was with respect to the degree of uh, the steps that we try to take. So let me get back to the section 5.8 and try to finish this. Yep. So yeah, this will try to execute. So are you guys with me? Or so let me try to start from 5.8 section. Here we have uh, the variance of the off policy estimators, which we are reducing. Uh, the other factors that we had are irrelevant. Uh, uh, we have taken only the 100 steps of a particular episode. Uh, and our discount factor is 0 in the sense that the G naught will be R1. Uh, so that doesn't make sense if we are trying to implement it. But yeah, this is simple really. Then they have considered this guy. And then the degree of partial termination, discounting, how they have considered discounting, then the initial return, how they have taken it to the degree of 1 minus gamma, uh, reducing the return of R1 plus R2 and so on, latter degree corresponding to the second step. That's simple really. And then the third step, with the square. So these are the errors in the sampling or the approximations that we get uh, with respect to the squared process that is being added. Uh, the partial returns are called here the flat partial returns in the sense that uh, when it is the discounted step is totally taken off. So uh, mm, absence of discounting. do not extend all the way to termination, but instead stop at call the horizon. So this is with respect to the termination of the episode at a particular horizon. This can be seen in this slide. I think let me try to pull up that slide. That's done. Yep, this is a kind of a forward view with respect to a particular horizon that we are trying to see. This is a TD lambda approach, but it can obviously be applied here too. So, just trying to, yeah, get a particular representation of that particular figure. In the next edition, this will be clear. Let me find this. Let's see. To call a laptop and programming. Iterations. This is the only figure that we have. Yeah. So we can also think of this like the flat partial returns in this particular horizon that we go on to. Uh, so this you can see the horizon that we have. And yep, this is the flat return. This is a simple derivation of the summation that is an alternate representation here. So this guy here, uh, with respect to the G bar from T to H, is the horizon, and G bar from T to T, this is the viewed as a sum of partial returns. Uh, so yeah, G from T to H only involves the rewards up to the horizon H. This is the ratio of probabilities up to H. So yeah, this is the ordinary importance sampling estimator that we take here. Uh, this is when we try to weight it with respect to the summation of these terms. This is the discounter where these two are coupled as this. Discounting are where importance sampling estimators. Yeah. It's simple really, and then uh, we can also reduce the discount rate to 1, uh, and then they will have no effect on the uh, so these and they will be the same in the off policy estimators. So this is the derivation of how we have uh, uh, the the discounting aware importance sampling estimators. Uh, these are the two. Uh, uh, this is the ordinary one, and this is the weighted one. This is the derivation with respect to the summation of this. I think so. This is clear. It's simple, really. It's just a how do we consider discounting the intuition behind this degree of partial termination? How can we how can we look that up? Uh, what discounting means in this case? So now we go on to the per decision importance sampling. Here, what they are trying to do is, uh, and this is based on the estimators of equation 5.5 and the 5.6 that we have seen earlier. Uh, this is the weighted importance sampling, and this is the ordinary one. And this had been reflected in the per decision one, in which the structure of a sum of rewards can be taken based on the uh, uh, how do I say it action that has been taken. So uh, mm, that's the kind of a per decision importance sampling ratio that it tries to give up to try to give. And here, what they are trying to do is the policies and the behaviors here with respect to the rewards. Sorry, the return in sense of t plus one. So, uh, uh, okay, that was random walk here, but it's finally we executed. It's taking time. This was my last execution that I had problems debugging, uh, but it's simply taking a large amount of time because of the debug parameters being logged into my ID. So it's just that case. Uh, uh, what they are trying to do here is this is the kind of off policy estimator. Uh, and this is the same kind of product that we have seen earlier with respect to the policies and the behaviors. The example I gave last time with respect to those auto driving, the uh, how do I say it? The important decisions that a self-driving autonomous vehicle might have to take depending upon the conditions or the of a particular uh, 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 thing that it sees in the future. The example that I gave was the difference between the how do I say it? If uh, you have a car that's driving at 80 miles per hour, and you have a bunch of school children that are crossing, uh, which of course might be some kind of a simulated condition, then uh, that autonomous vehicle like Tesla or any other might try to save those children by trying to uh, uh, get you off the road, get your car off the road. In that sense, uh, uh, there might be an accident on the vehicle that you are in. But yeah, the priority, how will it decide on the priority of what that decision should be? So uh, uh, how do we sample it based on the complete variance of the state space that we have, depending upon the trajectory we want? Uh, uh, some ethical considerations might be, uh, since the car is very well built to handle such kind of a accident, or most of the in most of the cases it will be safe. uh, yeah since uh, 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 how how do I put it? Those regulations put and the car has such safety features with respect to the airbags, and since those electric cars have batteries uh, that have low and the center of gravity is at the uh, uh, center of the car. If we try to compare it with an ordinary petrol or diesel engine, so there will be much greater chances of uh, saving the driver if it uh, tries to uh, how does it consider an option in which the driver might be compromised or the car might be compromised. So that was one condition that I thought of, uh, and how the rewards will be related there with respect to the policies and the behavior. Uh, of course, then the school children might take a precedence in the in trying to save them with respect to because the compromise perspective is much higher here. So yeah, that might be biased. Yeah, so these kind of conditions and other factors might be taken care of uh, uh, in this way. So uh, yeah, and in other robotic tasks too, this per decision importance sampling uh, might be like in a uh, uh, Go, and in the example of Go, in which uh, uh, to show what is important sampling is used there, but with respect to safety, estimates of sampling per decision, estimate a low variance in ordinary sampling, and yeah, based on the historical proposed policies and confidence levels of the particular. Then this is the inequality, Chernov's, and this is mountain car. Oh, this is the concentration inequality which they are. Okay, okay, this makes sense. This certainly makes sense. This is the conservative. Okay, okay, cool. I think so. This clears things up with respect to if you guys have a view of the trajectory. This is a very good representation of the importance sampling trajectory that uh, uh, for example, the autonomous vehicle example that I alluded to earlier, uh, which is the evaluation policy. This is the behavior policy, and what target policies will be like, the probability of the particular trajectory that it's trying to head. So uh, this will be the basis of the past. This is a simple equation that gives the uh, ratio of the uh, uh, target up to the behavior. So target upon the behavior, that's the same that we have considered here. So, uh, the per decision one has still the unbiased and the strongly consistent estimator, and it has the lower variance than the ordinary importance sampling. So uh, this might we can say that uh, are in the real world implementation, this might have a larger impact because of course the number of state spaces to choose from is small. uh, this figure kind of reflects what I was talking about, uh, based on the historical data, the proposed policy, and the confidence levels. So uh, okay. uh, so okay, let's just try to I will try to share all these slides and the per importance sampling ratios that I have discussed here. Uh, so historical data, the proposed policy, the confidence levels. These are the confidence bounds. So I was thinking of how this is lower. So since if we do not have a confidence bound there, so you can see we have these are the state spaces that we can choose from. Okay. And the importance sampling, if I draw a box, so these will be with respect to the time duration. So as you can see, if the variance here, I try to change the variance here. So that's the difference, uh, the per decision one as opposed to the ordinary importance sampling. This is the per decision one. So and then this GT tilde is the decision importance sampling idea that we took. Uh, and then we use this as an ordinary one too, uh, to try to put this there in. the equation that we have seen earlier. So what I think so here they have done is try to improve it based on the Chernoff Hoffman's inequality in the sampling space by the in the proposed policy that they are trying to take. So this is the kind of a sampling trajectory which tries to minimize it. This time, this is the concentration inequality, and they might have tested it. They might have hypothesized this theory on the mountain car example. So this is very specific uh, to this kind of a problem. Okay. It can be extended with respect to those other critical uh, 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 hmm, how do I say it? Points that we had alluded to earlier. And then, because these off-policy behaviors can be tuned to retrofit uh, your particular idea or your particular autonomous vehicle, if we are trying to uh, 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 think from an implementational perspective. So uh, that's very much beneficial there. Yep. So this was the end of the discount aware importance sampling and the per decision importance sampling ratios that we discussed. Uh, then yeah, we had 4 or 5 advantages of the Monte Carlo methods, which are to summarize it. Uh, uh, this is the first advantage. They use the optimal behavior directly from the interaction. Second, they can be used with the simulation. Third, it's easy and efficient to focus on uh, for a small subset of states, depending on the criteria, like in the per decision importance sampling ratios. And the fourth advantage is uh, that they may be less harmed by the violations of the Markov property. This this is a bit how do I say it? Uh, mm, mm, a kind of a drawback too, if we think about it from if we compare it to the TD approach that we will take care of in the next session. So yeah, because they do not update their value estimates based on the successor states. They do not bootstrap. So this might be a problem uh, in an online settings, yeah, or the critical conditions in which you try to how do I say it? Stop based on the particular condition that uh, your autonomous vehicle sees. So, yeah, there is the drawback with the TD, but yeah, it has certainly an advantage over DP. And then they discuss about the GPI. Then the sufficient exploration methods is an issue in the Monte Carlo. Uh, because we cannot, of course, take all the actions that can be taken. We cannot explore all the actions, and we won't be able to estimate the best. Other than that, they gave difference between the on policy and off policy methods. And mm, yeah, yeah. So this was all. And where did the term Monte Carlo comes from? It dates back to the Los Alamos physicist from the 1940s, which had some uh, complex understanding of the physical phenomena from the atom bomb's perspective. Uh, yeah, so from that it came along, and the convergence. Yeah, you can find it in other textbooks too. So uh, this was the maximum things. I would just like to allude to the slides respect to the Monte Carlo backups, the advantages. So yeah, next time we will be going through these slides. Uh, I, it will be much easier when we compare the TD and the Monte Carlo and the DP approaches, uh, and we look at the differences. I will try to present a difference between the same kind of like approach in different sorry same example using different approaches. What will be the difference? Then of course we will be taking a look at the SARSA tool. I think the SARSA is here. Advantages of the random walk. SARSA, yeah, SARSA and the Q learning. Then we will only double down on. Then the double Q learning approaches. Yeah, and the convergence properties of that. So yeah, from a mathematical perspective, this forms the basis of the things that we do. Uh, we will take a look at the relationship between DP, TD, and MC methods. So uh, please kind of like revise the original DP and uh, chapters with respect to the Bellman expectations and the Bellman uh, optimality equations, because they will come in handy when we discuss through it. Yep, that is it from my end. We didn't discuss Glee, the greedy in the limit of infinite exploration. I think so. Uh, in the book, they haven't. Didn't find a topic here. That's what I was waiting for. This is important. The Monte Carlo control policies with this guy. How do we reach this? Anyways, we can discuss this next time too. The rule and water sampling, DQ and roulette. Yep. Until next time, thanks everyone.